Let us start this lecture with a thought process from Rudolf Clausius, who gave this thought process in 1851, who says, in all cases where work is produced by heat, a quantity of heat proportional to work done is expended, and inversely by the expenditure of a like quantity of work, same amount of heat may be produced. So, if you look at what is this statement and what it will be, we will be discussing today in this class. However, let us recall as usual what we learned in the last lecture. If you recapitulate that, we started with the ideal gas law, which was very familiar with you, and later on we moved to van der Waals equation of state, which can be applied for the real gases. We have also seen that that law is good enough for not only the gases, but also for the liquid, but however, it will not predict well for the vapor and liquid mixtures. Later on we saw three equation of state which can be applied for real gases, but there might be several of them, but we have only looked at three. One is the what we call Benedict equation, and other is the Redlich and Kong equation, and another is Rubin and wave equations kind of thing. We have seen those are basically semi empirical relationships which are not having any theoretical basis. And later on we also discuss about virial equation, which is having basis of theoretical background, and unfortunately those coefficients like virial coefficients, like you can have higher order terms also, but the experimentally only the second order terms one can find out the coefficients, but later on. Therefore, it can be similar to an very simple form, but however, it may not be applied for all the cases. That is the limitation. Of course, there is more need to be work to be done for that, obtaining the virial coefficients for various gases and various what you call materials, and also this thing. Beside this, another thing we did, we looked at compressibility factors. By using compressibility factor in equation of state, you can take care of the real gases, and we have seen that a generalized compressibility chart on which most of the gases, rather large number of gases can be or large number of substances, not only gases, substances can be plotted in single plot, and we also learnt how to use that compressibility factor and chart for evaluating the properties. But today we will be doing little different, that as I told in the very beginning, we will be looking at what you call various relationship, various quantities, namely the heat and work and energy, right, through which a system interacts with its surrounding, right. But what are the relations between these things, what we are going to discuss today? Because whenever a system undergoes a process, right, during its interaction with surrounding, then there will be some change in the energy, and that change can be energy interaction can take place either by the heat or by the work. Now, what is the relationship that can connect all these quantities, that we are going to see. but I will just give you a little bit historical perspective. If you look at till 1780, when the Cleghorn gave a theory known as caloric theory. Before that, it was known that about the conservation of energy for mechanical system. But however, people were not having much idea about what is heat, right. So, Cleghorn is the first person to give a theory which is caloric theory. According to this, the heat is like an elastic fluid having no weight, and it is conserved. That means, you can, this heat he is saying is conserved. And later on, the Lavoisier in around 87, he also, you might be knowing Lavoisier is one of the greatest scientists. So, he also told that, look, this heat, whatever you call it, can be termed as a calorie. And that theory was very much being used and experimented by various people. People felt, look, this are, and number of work were being reported at that time, and it remains for a very longer period of time till like Joule come into picture, J.P. Joule. Of course, before that there was a what you call Thomson, who who happens to be a superintendent in the military in German, Munich, right. And while he was reboring the gun, he found out that this mechanical energy, is converted into, you might be knowing earlier days, even in India we are having very big barrel guns, and then you will have to put this kind of bore, the what you call gunpowders and everything, and then bore it. And while mechanical work is converted into heat, then he says that, look, it cannot be true that what caloric theory is talking about. And of course, he with a lot of his influence with what you call in Royal Society, at that time Royal Society was a very big thing, in the sense scientific body, and he tried to conduct experiment and also told, like, look, this is not right, and the mechanical work can be converted into heat, right. He gave that idea, but nobody really took his idea for quite a bit, maybe around 50 years kind of thing. And later on, the J.P. Joule, who was a very young person like you, like around 20 years old at that time, he conducted series of experiment, right, and he was not educated in a formal education system, and of course, he was being tutored by a very great person known as Humphrey Davy, you might be knowing. But he conducted series of experiment, like the caloric theory was established, but he demolished it by conducting series of experiments and related this work and heat, which is against the caloric theory, right. And what he did, he basically took a what you call container in which there will be some kind amount of water or fluid he took, right, and then he insulated this thing and put this paddle wheel, and paddle wheel can be rotated, and which is connected to pulley and this mass, and mass can be basically can be lowered against the gravitational field, right. And what will happen if I take this as my system, dashed line I have put, then what will happen? No heat is being transferred here, right, no heat being transferred here, and work being done or not, work is done on the system by this paddle wheel, right. And what will happen to this water? Suppose it is at ambient temperature to start with, and before the movement of this paddle wheel, then what will happen to its temperature? temperature will definitely will increase, right. And means this temperature is increased, that means the work whatever being put into the system by the paddle wheel, right, has been converted into heat. You can think of that way, right. Okay. And of course, one can evaluate how much it is there, and then by the work done potential energy, that is mass into gravity into change in the elevation or the height, right, and then one can evaluate. If you look at this process can be described in this, like 1 to 2. Let us say system has at station 1, and due to this work done it has gone to station 2. Okay. Now, what it did, he now remove this insulation, as a result, right, heat can pass through this, heat can go out of this, I mean all the side, then what will happen? Temperature will be coming back to the ambient temperature whenever it will attain the thermal equilibrium, right. So, the process can come from state 2, state 1, right. So, if you look at, that means the process started at state 1 and it some work is being done, and then some heat interaction is taking place and coming back to the state 1 again, and this process we call it as a cyclic process, right. And therefore, we can define a cyclic process as a process or a combination of process. Of course, in this case we are considering only one, but there might be several processes which we will see in whenever we are discussing about practical cycles like your Otto cycle, diesel cycles or Rankine cycles, right, by which a system returns back to its initial state, we call it as a cyclic. And he also conducted several other experiments. I will be discussing one of them more, like what he did, actually he took another system, like a system is same, but instead of what we call the paddle wheel, he put a resistance here and connected to a battery. And when this switch is on, then what will happen? The current will flow through and heat it, the water, and then temperature will go up, right. You can call this as a heat interaction, you can call it as a work interaction, we have already seen, right. And that is equal to W, we can say, because we have taken the full the system boundary I have shown here, it is including the heater, therefore, it will be work interaction, right. If I exclude the heater from the system, then it can be heat interaction. We have already discussed that earlier. So, this work is basically what you call E, I and T, where E is the EMF, I is the current and T is the time. So, certain amount of heat, and system again moves what you call state 1 to the state 2, and again when you remove these insulations, right, what will happen? Because temperature has gone up due to the heat, due to the work done by this electrical heater on this, the temperature of the system will go from ambient to certain temperature, right, it will be higher. And then when it will remove this insulation, right, I will remove this insulation and allow the heat to pass through this such that, and the temperature of the system will lower down, it will be lowered down till it attains the thermal equilibrium. That means, it will be reaching back the ambient temperature if it is started from the ambient temperature, right. And then you can trace the path like a cycle the way we did. That means, it is similar in nature, that what he observed, he did several of experiments and concluded, and formulated the first law of thermodynamics he conducted series of experiment, as I told, 1843 to 1850, 7 years he took to this experiment, which looks to be quite simple. You can say, look, why can't he do in 4 or 5 days or maybe 1 month, not something 7 years. And Joule concluded that net work done on a system is always proportional to the heat interaction, irrespective of the type of work interaction, because two type of work I have just now illustrated here or discussed here, but there might be several other work kind of work, right. And the rate of work done, he also varied this work, like let us say few what you call kilojoule, let us say, or I will say 5 kilojoule, I can say 50 kilojoule, I can say 500 kilojoule, like I can change that. And method of converting work into thermal energy, he did all these experiments and concluded that. And then, in other words, if a system involves number of work and heat interaction, then we can have that cyclic integral of the work is proportional to cycle integral of the heat interaction, and which is equal to cycle integral dW is equal to J cycle heat interaction integral of the heat J. J is your a constant, and in SI unit the J is basically equal to 1, and this we call it as a Joule's constant, and this is the basically first law of thermodynamics. Okay. Is it you people are aware about this? What you know as a first law of thermodynamics proposed by this thing is different than this, okay. But how, I mean it can be utilized, this first law of thermodynamics, we will see later on. So, if you look at, this is the equation and this is the first law of thermodynamics, right, that we say the cycle integral of heat is equal to cycle integral of the work. Keep in mind, this thing is valid, this expression is basically valid for SI unit, otherwise the J should come into picture. Okay. In case of SI unit, J is equal to 1, but in FPS unit it will be different. So, what it states? It states, that is the first law of thermodynamics, whenever a system undergoes cyclic change, however the complex the cycle may be, the cycle integral work is equal to the cycle integral of the heat. Rather, I would put this way little bit differently, which is the first law of thermodynamics, that is whenever system undergoes a cyclic change, however the complex cycle may be, the cycle integral of work is proportional to the cycle integral of the heat, right, because the J, the constant, comes into picture, that one can say also. So, this was firstly proposed by the great scientist J. P. Joule in 1851. Do not think that he was the only person who was working, there was another person, let me tell you little historical perspective, his name is Mayer, and he also working on this, but he could not propose this statement very with argument. He was having similar concept, but he was not having enough arguments and also the evidence, because what happened, he was also conducting experiment, but his son or the I think one of his child died, and then he could not really manage well, but later on he was very frustrated, he also tried to commit suicide, but he could recover, and then he was also considered as a proposer of this first law of thermodynamics. Credit was given to him much later, not at that time. He was having lot of agonies, he worked so hard, but however it was not recognized. So, and there might be several other people who might be working on this to that. So, the first law of thermodynamics is a generalization of several experimental data, right. Till date nobody has proved it to be wrong, right. But however, this law cannot be proved like a theorem what you do in mathematics and other things, right. It is on experimental basis. There is no fundamental like where you will look at it and work on it. See, it is the other way around. But however, people do even today might be trying to prove that this is wrong. So, therefore, there is always we always challenge the established concept and then go beyond it. So, that is the very important point you should keep in mind, that do not accept the thing what it is, but however, if it is true we will have to accept it. So, therefore, we can write it down as the cycle integral of the del q, that is the heat interaction, minus the cycle integral of work is equal to 0. This just I am putting over here, and this heat from the system, right, in this case, and this is work done on the system. It can be just opposite also. So, what we will do, that we will have to look at the sign convention again, because that is the work done by the system is basically positive, work done on the system by its surrounding, right, will be negative, and heat entering into the system, right, from its surrounding is positive, and heat is going out of the system to its surrounding is basically negative, and this you will be using. I can use just opposite of that, and also can manage and apply this first law of thermodynamics as well without any error, but one has to be consistent with that. So, what are the consequences of first law of thermodynamics, that we will see, right. So, whether we can say it is a heat is a path function from the first law of thermodynamics or not, that we will see. For that, what we will do, we will say that let us consider a cyclic process, like from the system from the state 1 is moving through the path A and also returning back from state 2 through the path B. This is one way of it is completing one cycle, right. I can apply the first law of thermodynamics for the cycle 1A 2B 1, and I can also apply the first law of thermodynamics from state 1A 2 and take another path from state 2 through C to state 1, right. I can have, yes or no, I can apply the first law of thermodynamics for both the cycle between two state points, between the 2 points. So, applying the first law of thermodynamics to the cyclic process 1A 2B 1, that is here 1A 2B 1, what we will do? We can write it down, that is delta q 1A 2 plus delta q 2B 1, that is integral we are saying, right, in this path is equal to the cycle integral of the work, I am like in the total, and if you look at it consists of 2 paths, the work done in the path 1A 2, the dW, and work done in the path 2B 1, right. We are considering now this what you call path 1A 2B 1. Similarly, we can also write down or rather apply the first law of thermodynamics to the another cycle, but between the 2 states, that is 1A 2 C 1. Right. So, that is the if you look at this term is same as that of that is the for path A 1 2, and of course, the heat this path 2 C 1 is different if you compare the equation 1 and equation 2, and work done also is basically dW path 1A 2 and 1A 2 here both are same, and these are 2 are different. and what we will do, we will basically subtract this equation 2 from the equation 1, and if I do that, what will happen, this will cancel it out, because I am minus, I can put a minus here, I am just subtracting. So, this will cancel it out. Similarly, I will put a minus here and this will cancel it out. I will get dq for the path 2b1 minus dq for the path 2c1 is equal to dw minus for the path 2b1 minus dw 2c1. So, from this we can deduct, we can deduce it, right, that what is that thing. Let us look at what happens to work. Is the work done for path 2b1, will it be equal to the work done path 2c1? Is it possible? No, because if you look at, if I take this diagram, the path, the area, for one case area will be this one, right, this area for path 2b1. For path 2c1 there is another area added. So, it is not same. So, it is different. So, if it is different, that means we can say that this, the work done in the path 2b1 minus work done in the path 2c1 is not equal to 0. That means, the work done in the both the path are different, I have already told you. Then we can, from this we can say that dq, because this is not equal to this portion is not equal to 0, right. So, therefore, the work done, the heat interaction between the part 2b1 minus the heat interaction part 2c1 is not equal to 0. That means what? Because it is between the two state, 2 and 1 state is same, like it is for both the path. Therefore, from this we can say that the heat interaction for the path 2b1 is not equal to the heat interaction between path 2c1. Therefore, we can call it basically heat interaction is not a point function, rather it will be dependent on the path. Hence, as it is not a point function, it cannot be a property of the system. That we have already earlier discussed, but now using the first law of thermodynamics, we can prove or you can deduce that look, it cannot be a what to call point function or a property of the system, rather it is a path function. So, now let us look at another aspect of that. So, before doing that, like we need to know that in most engineering application, non-cyclic processes are encountered very often, right. What we have derived till now is basically the first law of thermodynamics for a cyclic process, right. If the process is not cyclic, then you can't really use it. But as the engineering application, processes need not to be cyclic, right. For example, in the what to call a system, let us say there is a what to call cylinder, gas cylinder, and it is being leaked out, right. Can I get it back to the original? So, it needs to be put the work into that, it is not cyclic. However, there are several cyclic processes also, as I told, like your automobile engines, right, it is cyclic, it is go on working and then giving heat and other things it is doing. So, now we need to see how we can apply the first law of thermodynamics, which we have discussed just now, meant for the cyclic process can be extended for a non-cyclic process. For that, we will have to use the same equation, that is for the like for the path 2b1 heat interaction minus the path 2c1 is equal to work interaction 2b1 minus work interaction 2c1. By rearranging this equation 3, what we will do by this, basically we will take this term to this side and this term I can take to this side, right. So, if I will do that, what I will get? I will get 2 dq minus dw for the path 2b1 is equal to dq minus dw 2c1, right. And this term, if you look at dq minus dw, is basically from this statement, one can say that it is does not depend on the path. That means, the q minus w for the path 2b1 is equal to q dq minus dw for path 2c1. It is this term, the heat and minus the work, is basically this term is independent of the both processes 2b1 2c1, and this is basically we can call it a point function or a property of the system, right, because it depends only on the initial and final state, right. It does not depend what path it takes, whether the path B between the state 1 and 2 or C or D, whatever it is, we of course, we have considered only 2 path, and these properties what we call is basically the internal energy, right. And when we say that, then we say that energy is a property of the system, right, because this term we are saying dq minus dw is nothing but dE, and dE is exact differential. It does not depend on the path, it depends on the point, or rather it is a point function. So, it is a property, and this equation, if you look at, you can apply very well for the what you call non-cyclic process, right. Okay. And this you are aware, okay. This is generally whenever you say that tell me the first law of thermodynamics, people say that dq minus dw is equal to dE. What is the dE? dE is basically the total energy stored in a system, like E will be consist of internal energy, kinetic energy and potential energy, and this is the microscopic form of energy. We have discussed extensively on that, right. Whereas, U is the internal energy, like, whereas the kinetic energy and potential macroscopic form of energy, right. So, and most of the cases, kinetic and potential energy are neglected because of being small. Therefore, you always say that dq minus dw, if this Ke and Pe is small, then I can write down basically dq minus dw is equal to du when Ke is almost small, very negligible, and Pe, right. So, we will be using this application, and therefore, what you call net change in energy is equal to net interaction between work and heat. So, therefore, energy interaction between system and its surrounding can take place in through two mode. One is work interaction, other is the heat interactions. So, I have already talked about that. Let me again repeat that energy can be exchanged between system and surrounding by two ways, either by the work or the heat. So, now let us look at for an isolated system. Like isolated system means we will take a very rigid kind of a chamber where there is insulated, this is insulated. Insulated means it will insulate to such an extent that no heat will be going passing through the its boundary, right, and there is no work done. Of course, it is rigid and there is no other shaft work and other things in this case. There might be like PDV work or the boundary work, and there might be also the shaft work or some other form of work like electrical heating and other things, but nothing is there. So, therefore, dq and dw is equal to 0. So, when dq and dw is 0, then first law of thermodynamics, it turns out to be dE is equal to 0 between state 1 and 2. So, therefore, the energy at state 1 is equal to energy at state 2, provided it is an isolated, that means no interaction like either work or the heat is taking place. And this you can state as energy remaining constant, and which we always say that energy can neither be created nor be destroyed, but can be transferred from one form to another, and that is valid only for an isolated system, not for all systems. Okay. So, that is the principle of energy conservation, which we will be using in several places, like in your application we will be using that. And as I told that macroscopic forms of energy is kinetic and potential energy, which can be easily converted into work. In contrast, the microscopic form of energy, that is internal energy, which is due to the molecular motion, cannot really be converted into work. It is quite difficult to do that, and that is why we will have to find out various ways and means of converting the internal energy into work. And generally, the heat is being employed, heat engine is being employed to convert the internal energy into work, right. But what is a heat engine? What do you mean by that? Heat engine is basically a cyclic device which absorbs the energy from its surrounding and does certain amount of work. That means, it has to absorb certain amount of energy. I mean, either it can be heat or it can be any other form, right, and then does certain amount of work. Whether it does all the work, I mean convert all the heat into that, into the work or not, that question need to be right to be looked at. So, therefore, as it is cyclic device, therefore, we can apply this dq for the cycle integral minus the dw is equal to 0, and dq is equal to the dw. Of course, the cycle, this symbol is basically cyclic integral, right. So, if you look at, is it really possible to have a engine, heat engine, which can absorb certain amount of heat, but will not do any work. In other words, is it possible that without absorbing any energy from its surrounding, can we have a engine? And that kind of imaginary cyclic operating device, which would produce the work continuously without absorbing any heat from its surrounding, is known as perpetual motion of machine of first kind, right. You might not be remembering, few years back there was a person who is maybe a school dropout, but he was a what to call a technical nerd kind of things, and then he started saying that he could produce some kind of oil, without really doing this. Raman Pillai his name, and there was a lot of euphoria in this. He could get something from the, kind of this thing that is similar to that. Of course, if you look at this concept has been captured this by the several people who try to work, and till today also some people will be thinking, look, I can get energy. You might be knowing that the several mystic people or the spiritual prophets, they say, look, I will get something out of nothing, like let us say I will get one rasgulla out of nothing, how it is possible. So, it is similar to that, that means you do not have energy and you will start working. For example, if I will not take food, can I work really? Yes, I may work for few hours. You might be knowing that several people like who go on fasting and still work, but those they use the stored energy which is there already in the body. Because if you go beyond maybe a month of fasting, you can't really do much work, right. So, therefore, it is what you call violating. Let us see how it is violating that. For example, if I say that there is a without any observing, for example, like observing any heat, you need to absorb certain amount of heat and then do some work, that is a basically heat engine. Suppose I say this is 0, then that is known as perpetual motion machine of first kind. If somebody of could do that, it will be great, like we need not to do a lot of things, right, without absorbing energy. Now, is it possible to have a perpetual motion of first kind or not? That what we will have to do? We will have to apply the first law of thermodynamics and say, look whether it is possible or not, because the several device you will find people have put forwarded or they are claiming that they are having a machine. If you look at your internet and you will find out like, oh, there are several of them, even till today also some people will be trying, but it violates the first. Let us see how why the perpetual motion machine of first kind is not possible from the first law of thermodynamics. So, I say that cycle integral of dq is equal to dw, and if this is 0, right, 0, that is saying that without absorbing any heat, right, from its surrounding, then what will happen? The work done will be 0. Okay. Work done will be 0 over a cycle. So, therefore, it is not really possible to have a perpetual motion of machine of first kind, right. Let us look at other way around, that means reverse, that is the work being done on the system. Let us say there is a engine, right, by the surrounding, and there is no heat being dissipated out. Like if you look at, heat has to be dissipated out here. Whenever work is done, some heat has to go out, and if it is not, then that is also not possible if it is 0. But let us look at some of the examples where you may think, look, I can have that, like I can have a perpetual motion of a system. So, let me just tell you also that till date no such perpetual motion of first kind is created, although there are several claims are being made by various people starting from the Joules onwards, but nobody is successful in doing that. So, let us consider a piston and cylinder kind of arrangement where it contains, let us say, gas at pressure P 1 and V 1, and where P 1 is greater than the P 0. Okay. You can say that, look, let us have a latch here, right, which will stop. I will remove this latch, I will remove this latch, right, and then what will happen? Piston will go up or not? Piston will go up. That means, if I connect this piston to a rotary motion or something, and then I can make it to rotate, some work can be done, right. Is it some work being done or not? Because if I put some weight right here, and then it is going against that, and then some work being done, right, piston can be moving up. Then can you call it as a what you call, because work being done, you are not giving any heat. Are you giving any heat? Energy? No, no, but work being done. Can you call it as a perpetual motion of machine of first kind? Is it yes or no? See, there is a gas is here at high pressure, and then you will and this is a lower pressure, that whichever is acting as a latch, I will just remove it and then it will be expanded, some work being done, yes or no. Now, I have not given any heat here, that means this is a perpetual motion machine of first kind. Am I right or wrong? actually it is not, because it is not cyclic process, and this process will go on till it reaches equilibrium with the P naught. P 1 goes on decreasing till P naught. That means, where I am getting energy, the energy is stored here, and that is being expanded and converted into the work, right. And after that you cannot really come back to the original position. So, therefore, it cannot be. So, and hence such a device is not a perpetual motion of machine of first kind. In summary, what I can say is that energy is a property of a system, right, that we have seen. Energy of an isolated system is conserved. Impossible to have a perpetual motion machine of first kind. That means that you can do the work without absorbing any energy. Okay. So, therefore, this is the things what we have seen. Let me what you call just tell you that we have seen the first law of thermodynamics is applied for the what? For cyclic process. But however, we have learned that derive an expression from the first law of thermodynamics for an which can be applied for non-cyclic process, that is dq minus dw is equal to du or dE rather, because if I say internal energy, that means it is basically change in kinetic, change in potential energy is negligible or almost equal to 0. So, therefore, that equation is what we have we have derived, that is dq minus dw is equal to dE. This is applied for non-cyclic process. Right. So, therefore, this we will be using it for various problems to solve and other things that we will be discussing maybe in the next lecture. Thank you very much, and we will continue also maybe after this.